video, I had discussed about definition of metric space with example. In my previous video, I had seen some metric which is induced by norm. Also, I had seen some different type of metric which does not induced by norm but be a metric space. But earlier video, I have discussed only metric on the space Rn, Cn, etc. Today I will see metric space on all real valued function which is defined of closed interval AB. And we all of us know when C of AB, then norm defined as supremum of absolute value of fx where x belongs to AB. Since this is the norm, so here the metric which is induced by this norm would be d infinity f comma g, which is equal to norm of f minus g infinity, which is actually supremum of absolute value of fx minus gx where x belongs to AB. And the picture is such type: consider this function is fx and consider this function is gx. Then this distance be the distance between fx minus gx. Then the norm here, the metric space defined as supremum distance of these two functions. Are you getting? Let's verify. D infinity f comma g is a metric space. First condition always be equal because d of fg equal to here defined as x belongs to closed AB absolute value of fx minus gx, and this supremum distance of these two functions always greater than equal to 0. Second condition, d of f comma g equal to 0 means obviously supremum x belongs to AB, absolute value of fx minus gx equal to 0. That means supremum distance of these two functions is equal to 0. And this equal to 0, this supremum equal to 0 means obviously absolute value of fx minus gx equal to 0 for all x belongs to AB. And that imply fx equal to 0 for all x belongs to AB. And since fx equal to gx for all x belongs to AB, that means actually f is identically equal to z. Third condition of metric space is symmetric property. This is always obviously true because d of fg by defined function this is equal to supremum of x belongs to f absolute value of fx minus gx, and absolute value of fx minus gx always similar to absolute value of gx minus fx. That means supremum x belongs to AB, absolute value of fx minus gx always similar to supremum x belongs to AB, absolute value of gx minus fx. And this is actually d of g comma f. That means d of f comma g is equal to d of g comma f. Obviously it will satisfy the triangle inequality. And for triangle inequality, consider three function f g h belongs to CAB. Then obviously distance function of f g equal to defined as supremum x belongs to AB fx minus gx absolute value, and we can write this as absolute value of fx minus hx plus hx minus gx. Now apply the addition property, then this would be less than equal to supremum x belongs to AB absolute value of fx minus hx plus supremum x belongs to AB absolute value of hx minus gx. And this is actually nothing but d of f with h, and this is d of h with g. That means d of f with g always less than equal to d of f with h plus d of h with j. Therefore, triangle inequality also has satisfied. So, all property of matrix has satisfied. So, D infinity is a metric space. Also, there exists a interesting theorem. If we consider sequence of function in this metric space, then this sequence of function always converges uniformly to the function f on the closed interval ab if d infinity fn comma f means, we all of us know d infinity fn comma f means supremum x belongs to ab, absolute value of fnx minus fx, where for all x belongs to ab, if this distance converges to 0, we all have, and this is actually I had seen in sequence of function lecture, this is actually the mn. When this mn tends to 0, then the sequence of function with respect to d infinity metric obviously be converges to the function f. And this converges is uniformly converges. Now we can define another type of metric space in CAB. In Rn or Cn, I had seen the D1 metric space or 1 norm. Similar to Rn or Cn, here we can define D1 f with G as, here the metric space defined as integration a to b absolute value of fx minus gx dx, where for all fg belongs to CAB, and this matrix is induced by the norm 1, where norm 1 means norm of f1 equal to integration a to b absolute value of fx dx. Similarly, we can define the P metric space similar to Rn or Cn, dp f comma g equal to, since here d1 defined as integration means Riemann integration, then dp would be such type integration a to b absolute value of fx minus gx to the power p over 1 over p, where p greater than equal to 0. This is the dp metric space, which is induced by this norm integration a to b absolute value fx to the power p dx to the power 1 over p, where p greater than equal to 0. And this proof is similar to d infinity metric space. Just try to answer. This proof is obviously very important but similar to the infinity matrix. So, I leave it for my viewers also. This space is actually called capital LP space. Actually, capital LP space means set of those functions which constructed this norm and this norm be finite. Actually, this space is very important for higher study. Here one thing very noticeable. This is capital LP space, not small LP. Small LP is different. Now I will define a metric space on a sequence. First, LP space. LP space equal to xi1, xi2, xi and so on, such that summation I equal to 1 to infinity absolute value of xi I to the power p less than infinity, where xi I are scalars. Then we can define a metric on LP such type d of xy equal to summation j equal to 1 to infinity xi I minus eta I to the power p to the power 1 over p, where p greater than equal to 1, where the element x be the member of xi I and y be the member of y eta I, which belongs to LP. That means LP means actually summation I equal to 1 to infinity xi I to the power p less than infinity means set of all convergent series. I will verify this is the metric space. This is also easy type proof. Here x equal to xi I, which belongs to LP means obviously summation I equal to 1 to infinity xi I to the power p belongs to infinity and y equal to eta I belongs to LP means obviously summation I equal to 1 to infinity eta I to the power p less than infinity. Then obviously d of xy greater than equal to 0 because this is the absolute value. This term is absolute value, that means always positive. Then apply the summation to the power 1 p to the power 1 over p. This term, since this is the positive term, so all term be obviously positive. That means since this is the d of xy, so d of xy obviously greater than equal to 0 for p greater than equal to 1. That means first condition has satisfied. And second condition, when x and y both same, then obviously this sum always equal to 0. D of xy means this sum equal to 0. That means from this line it implies summation I equal to 1 to infinity absolute value of xi I minus eta I to the power p equal to 0. And since sum of is positive term equal to 0, that means obviously is term equal to 0. And from this line, obviously absolute value of xi I minus eta I equal to 0. That implies xi I minus eta equal to 0. So xi I equal to eta I, and since xi I equal to s I have considered and eta equal to y, so x equal to y. Are you getting? Condition, if we multiply this by minus, then this would be eta I minus xi I to the power p summation I equal to 1 to the infinity to the power 1 over p. And this is always same because here the absolute value. So, and this is obviously d of yx. That means d of xy always similar to d of yx. Okay. Now I will see the triangle inequality. For triangle inequality, consider d of xz equal to summation I equal to 1 to infinity absolute value of xi I minus omega I to the power p to the power 1 over p. Here consider it x equal to xi I and wz equal to omega I. Then obviously similar to before, we can write this as at eta I and subtract minus eta I. We can write this expression. Now using mean coaxy inequality. By this inequality we can tell I equal to 1 to infinity xi I plus eta I to the power p to the power 1 over p less than equal to summation I equal to 1 to infinity xi I to the power p to the power 1 over p plus summation I equal to 1 to infinity eta I to the power p to the power 1 over p. Now using this inequality here, then by this inequality we can tell this is less than equal to these two term. This term less than equal to these two term. By this inequality we can tell. And obviously this mean d of xy and this mean d of yz. Then d of x comma z less than equal to d of xy plus d of yz. Are you getting? OL. Means all condition of metric space has satisfied here. Obviously, LP be a metric space. This space is very important for higher study, also for any competitive exam. LP space. LP space means set of those sequence can be either real number or complex number, because xi1, xi2, xin can be belongs to R or complex C, such that the series which is constructed by this sequence always convergent. This is actually the LP space. That means when p equal to 1, then this space would be L1, and L1 means actually set of those sequence xi1, xi2 up to xin, such that absolute value of the series be convergent. This is the L1 space, and if you want to find L2 space, then this would be set of those sequence xi1, xi2, xin, so on, such that summation I equal to 1 to infinity absolute value of xi whole square less than infinity. This is the L2 space. Are you getting how we will find this space? Oh well. As for example, if you consider the sequence xn equal to n, then is this sequence belongs to L1? Notice, L1 means we have to find absolute value of n. Here n equal to 1 to infinity. This series converts to infinity. So, this sequence cannot belongs to L1. Are you getting the idea? Well. Similarly, if you consider xn equal to 1 over n, then the series, we all of us know, absolute value of 1 over n is divergent series. That means it converts to infinity. So, this not belongs to L1, but is this series belongs to L2? Notice, L2 means this would be absolute value of 1 over n square. And we all of us know 1 over n square, this series is convergent. So obviously this series tends to 0. That means this is belongs to L2 but does not belongs to L1. But if we consider the sequence xn equal to 1 over n square, then obviously this belongs to L1. Are you getting the idea? Oh well. And since 1 over n belongs to L2 but does not belongs to L1, that means we can tell L1 actually contain L2. And if we consider p equal to infinity, then this is set of those sequence whose supremum value less than infinity. That means set of those sequence which are be bounded. This is the L infinity space. LP means set of all convergent series, and L infinity means set of all bounded sequence. So, the metric which is induced by norm L infinity, this would be supremum I belongs to n, absolute value of xi minus yi. And this proof is very easy type proof. This type of proof I have defined more times. Okay, I will define one new metric space, induced metric space. Induced metric space actual idea is let X be given metric space. Now I will define one new metric space which is denoted as D star on the set X using the metric main metric D. Then D star is called induced metric. As for example, consider XDB metric space and define the new matrix which is denoted as D star, which is defined also this space X cross X to R, and the new matrix D star is defined as minimum of 2, D of xy, where D of xy is original matrix. Now we have to prove D star be a metric space. Okay, and the proof is such type. Since 2 greater than equal to 0 and D be a matrix, so obviously D of xy greater than equal to 0. That implies D star xy greater than equal to 0 for all xy belongs to the space X. Second condition, D star equal xy equal to 0 and D star xy equal to 0 if minimum of 2, D of xy equal to 0 and this term equal to 0 obviously when D of xy equal to 0, because otherwise 0 cannot possible. When this term be 0, then we can tell this minimum, because this is the minimum of 2, D of xy. When this is equal to 0, then we can tell this value would be equal to 0. And obviously D of xy equal to 0 means x equal to y. And this condition is obviously if and only if condition. If x equal to y, then obviously D of xy equal to 0. That means second condition also has satisfied here. Third condition, third property, D star xy equal to minimum of 2, D of xy. Since this is metric, we can tell D of xy equal to D of yx. And this is actually by definition is nothing but D star xy. That means third symmetry property also has satisfied. Now we have to prove the triangle inequality. And the proof of triangle inequality is same as the proof of discrete metric. Here we have to prove D star xy belong less than equal to D star xz plus D star zy, where x, y, z be the element of the space X. By definition, we can tell D star xy less than equal to 2 and D star xy less than equal to D of xy, because D star xy is minimum of this two value. Case 1, consider D star xz equal to 2 or D star zy equal to 2. Then obviously D star xy less than equal to 2, because if we consider this is 2 or this is another number, but obviously this value would be less than equal to 2. Also this consider 2 or this any another number, then also this would be less than equal to 2. 2. Consider D star xz not equal to 2 and D star zy not equal to 2. Then D star xz obviously equal to D of xz and D star zy obviously equal to D of zy. Then by definition D star xy would be less than equal to D of xy, and since D be a metric, So by triangle inequality we can tell d of xy less than equal to d of xz plus d of zy, and d of xz mean d star xz and d of zy mean d star zy. That means d star xy is less than equal to d star xz plus d star zy. That means triangle inequality has satisfied here. Are you getting? Well, that means obviously d star xy be metric space. D star xy be new matrix which is actually induced by this D metric. Are you getting? Well, if we define d star as a maximum of 2, d xy, then is it metric space? Just think at first. If we consider d of xy equal to 0, then maximum of d star xy means obviously 2. That means d star xy cannot be equal to 0. So we cannot take here maximum value. Are you getting why this type of d star is not a metric space? Well, today I will stop here, and in my next video I discuss this topic elaborately because this topic is very important. But at first I will highly recommend you, if you don't see my previous video, please do see my previous video at first. Then today's video and next video will be more easier. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel. Thank you so much.